Welcome. In this session, we'll formulate our simplified GPS problem as a nonlinear least squares problem, and then we'll consider an extension of one of the examples that we used in the very start of this course into a more complicated problem that can also be solved using nonlinear least squares. So our simplified version of the GPS is that for satellite I, and we're going to assume that the speed of light is constant, which is not a completely appropriate assumption, but in the reference material for this class, you can find more details on that. We can represent S sub I as the time that this message was sent from the satellite. We can say T sub I is the time that the receiver got it. So each one of these we're assuming has a really good clock. It's some kind of atomic clock, for example. The pseudo range is then given by the receiving time minus the sending time multiplied by the speed of light, and then that will give us the reading. So this is what we're going to use as the reading. There's an additional term having to do with clock offsets that we'll simplify out for this description. X sub I is the 3D location of the satellite at the time that it sent the message. So the satellite has an understanding of its own orbital mechanics, and it can then tell us in 3D where it is. So what we'll do is each of our model functions will be the unknown location of the receiver minus the location of the satellite, and then this is a norm. So because it's not a squared norm, this is going to be a nonlinear least squares problem. Our objective is we want to find a stationary point that will be the estimated location of the receiver. So when we do this, I encourage you to take these functions, write them out, and actually find this gradient for yourself. So the gradient of each one of these will be the transpose of the difference between the proposed receiver location and the satellite location at the time of sending, and then we transpose that so that it's a one form, and then we divide it by the ordinary L2 or Euclidean norm of that distance. So that each one of these will be a nonlinear function. The Jacobian is then the matrix of the individual gradients, and that is given by taking these, and each one of these gradients is a row. So this is the gradient for model 1, for model 2, and so on until we get the gradient for model M. We could use the Leavenworth-Marquardt algorithm to solve this GPS problem, and the illustrations that were in the session for the start of this lecture were computed using that. At the very, very start of this course, we looked at a simple 2D Fermat problem, and that was to find the geometric median of a given set of points. Well, this could be in 2D, 3D, it could be in n dimensions, and these might be weighted differently. That is, we may have a different relative importance of the different distances. So the Weber or Weber problem is we'll scale each one of our model functions that, for example, was like the GPS, and it'll be by some strictly positive number b sub I. We can gather those into a diagonal matrix, and then the objective would be, the objective of the nonlinear function would then be we scale each one of these gi's by the bi, and I can write that as a matrix vector multiplication, and then we take the squared norm, and then we may or may not have the half term in there. And we can solve this using either the Gauss-Newton or the Leavenworth-Marquardt algorithm. So what's our summary of this lecture? Well, nonlinear least squares has individual data and individual models. The model functions may depend on additional data, such in the GPS case, on the 3D location of the satellite at a moment in time. We could perform a local linear approximation of each model because we know that we're solving the minimizer, we're locating the minimizer using an iteration. The Gauss-Newton method alters the descent by taking this local linear approximation, and the Leavenworth-Marquardt is both altered descent and an alteration itself of the Gauss-Newton algorithm. So The global positioning problem and the Fermat-Weber problems are very easily formulated as nonlinear least squares problems.